Hi, this presentation summarizes the functional requirements set up for the last part of our compulsive coursework plan, where you are required to develop a simplified boundary scan test infrastructure. After watching this presentation, I hope that you will be able to describe those functional specification requirements, also to identify the main design tasks and how you can divide them among the group members, and finally that you will be able to explain how you can start the development work. The proposed BST infrastructure comprises two stages. The first one addresses the three mandatory operating modes defined in the IEEE standard. External test, where the boundary scan cells disconnect the pins from the internal circuitry. Bypass, where the boundary scan cells operate in transparent mode. And sample preload, where it is possible to scan test data to and from the boundary scan register while the boundary scan cells continue to operate in transparent mode. Stage 1 is where you will spend most of your time, so it accounts for 80% of your grade in this assignment. Stage 2 accounts for the remaining 20% and asks for an optional operating mode called override, where a pin is stuck at a given logic value. This optional mode could be used to validate fault tolerance features, since we could force a stuck fault at any pin and check if the system continues to operate undisturbed. I have represented in this slide the recommended codes for these boundary scan instructions. An important aspect is to avoid gated clocks. Always use a free running clock for every flip-flop in your design. This slide shows an overview of stage 1 and offers a good representation of what you are asked to develop. Since the core logic of the circuit is not relevant for our purposes, I've just considered it as a series of identity functions. This representation also calls your attention to the fact that we will be dealing with a hierarchical design. You will have to describe the circuitry inside the boundary scan cells, which are grouped together in the boundary scan register, which is then one of the blocks comprised in the top-level boundary scan architecture. And the boundary scan cells are not just reused to build the boundary scan register. Actually, the instruction register cells are a simplified version of the boundary scan cells, and the bypass register cell itself is a simplified version of the instruction register cells. So reusability of building blocks and hierarchical design are two key issues for this assignment, which you should consider from the very start. Before moving on to the next slide, I leave you this question. In the light of what you have learned so far concerning finite state machines with data path, would you see the boundary scan test architecture as an example of this type of circuits? You should consider design verification scenarios at every level, from the very bottom level, dealing with single test cells, to the top level, where you have the whole architecture ready for simulation. Well, you will be able to figure out your own test benches for the bottom level, but I'd like to propose two specific scenarios that you should all consider when recording the presentation of your work, for showing these simulation waveforms and explaining where these operations take place. In the case of stage 1, you should start by resetting the BST infrastructure and checking that the test logic behaves as expected when the tap controller is in the test logic reset state. Then you should check that the external test instruction works as expected, and finally shift in the bypass instruction and check that it also works as expected. The design verification scenario proposed for stage 2 is similar, but in this case we will shift in the override instruction to check that it works as expected, and then shift in the bypass instruction to check that all pins return to their normal operating mode. The specific steps for this proposal are summarized in this slide, and you can check them in more detail when you get to this part of your work. Here's a key aspect to succeed. Simplify whenever you can. This is not a complex assignment in terms of VHDL, but you will need to spend a good deal of time understanding how the embedded BST architecture works. And this is where the first simplification applies. You are allowed to relax compliance with the IEEE 1149.1 standard, but only in the case of the 3 rules referred in this slide. First, you can keep the test data output pin active at all times. Second is you can make all events synchronous to the rising edge of the clock. And third, the current version of the standard splits sample and preload in 2 instructions, but you can use a single sample preload instruction which takes care of both operations. Second simplification, designing for reusability is an important principle. Start by reusing the description of a D flip-flop with synchronous enable to design a boundary scan cell that uses the same free-running clock in the 2 memory elements, the one in the input stage and the one in the output stage. This will be your first challenge, but not really difficult to overcome. Make sure that you build a small test bench to check that it works as expected, and then you will be ready to proceed to the second module, where you will put together 6 boundary scan cells to build the upper level boundary scan register. Do another test bench at this level and make sure that everything is working properly. Then take care of the instruction register cell, which is a simplified version of the boundary scan cell, and follow the same approach, and so on. Always work bottom up and never move to the next level before simulating. Third simplification, I have already mentioned it, the need to simulate every block before proceeding, but there are 2 other design rules that you should enforce in your work. Draw a schematic representation of your circuits, a schematic diagram, or even a block diagram as you move up. And last but not least, name every signal appropriately and coherently. Your work will be so much simpler if you are able to know exactly where each signal is located and what it does by simply looking at its name. Take this example. This is the control signal for the multiplexer in the capture shift stage of the boundary scan cells. And finally, I leave you with the usual roadmap to carry out your assignment and prepare your final deliverables. I will just highlight the first and foremost point referred here. Learn the details of the boundary scan test architecture. There's plenty of information online, but please feel free to share your doubts in the course forum. And recall that you have to submit your deliverables by 11:59 p.m. on Monday, November 30th. Thanks for your attention.